Live. Hello, friends. Welcome to another Relatorium seminar. It's a relaxed Friday evening here in Tallinn. And we have with us today Professor Paweł Sobociński. So what is today's talk about? Most of us, when we hear the word mathematics, we think of numbers or like scary symbols. But what if someone tells you that you can do mathematics using pictures, right? And most of us will be skeptical. But to convince you, like we have here with us Professor Paweł Sobociński, expert in string diagrams, and he's going to tell us how he fell in love with string diagrams and his research adventure. So, Paweł, I have a question for you. What made you choose this topic today?
Well, I thought about what I should talk about, and I think sort of typically when we give talks, we talk about a particular result, right? We want to, let's say, present a theorem or present some kind of theoretical framework or an artifact. So you kind of build back the talk from what you try to present, which actually doesn't correspond to how the research happens, right? Because the research that happens, the journey that gets you to the result is very different to the way you present it. So kind of, and I've always given talks that way, right? So I've always thought, okay, my talk needs to end with this theorem. And so therefore I need to structure the talk so that the talk builds up to that point, right? Because you're trying to tell the story of that result.
Yep.
But instead, in this seminar, I thought I'd try something completely different. So this is going to be kind of like more of a chronological story of how I started this, which was kind of unexpected. It was one of the more weird things that I've done in my research career. But then again, it was also the most interesting and the most exciting and sort of one of the coolest personal experiences that I've had in doing research. So yeah, so I guess it's I'm going to try to kind of present things how I came to them and sort of try to share some of my excitement as I was discovering this for myself.
That sounds wonderful. We don't get to hear these sort of talks in usual math seminars. So
No,
this,
that's true. Probably for the best, because as I was doing these slides, I felt that maybe it's going to come across as a bit self-indulgent, right? Because it's very me. But let's see. I'll give it a go.
yeah, thank you. So let's welcome Professor Paweł Sobociński from Tallinn University of Technology. The floor is yours, Paweł.
Okay, thank you, Priyaa. So yes, so this talk is going to be about how I discovered string diagrams. So I'm going to tell you first about what I was doing about 15 years ago. So I really like this model of Petri nets as a model of computation. So Petri nets were originally introduced in the 1960s. They're this kind of a diagrammatic model for concurrency. They used in all kinds of different applications, including modeling of chemical reactions, including modeling of concurrent systems in computer science. So they're kind of everywhere, but they have a combinatorial definition. They've always been kind of considered in a monolithic way. So I was trying to sort of come up with ways to decompose them and understand the behavior and sort of a component-wise fashion. Okay, so maybe I should start by explaining. I guess Petri nets are not that well known for mathematicians. So I'll just give you a little explanation here. So here we have a picture of a simple Petri net. So you see that this Petri net has kind of two types of things. It's got circles and it's got these rectangles. So the rectangles are labeled from T0 to T4. And some of the circles have black tokens on them. Okay, so these tokens, you can kind of think of them as resources, right?
Okay.
And so the squares are called transitions, and transitions take resources and produce resources somewhere else. So at the moment, this Petri net is ready to fire T4, right? Because T4, you see the arrow that's leading from the circle to T4 has a token on it. So at this point, T4 can fire, And when it fires, it's going to sort of consume that token and produce a token at the place where there's the output. Okay, so basically this happens. Okay, and you can see now that we're in a place where now T3 has all of its resources that it needs to fire. Okay, so T3 will fire. And now T4 can fire again. Now T2 can fire, T3 can fire, T4 can fire, and etc. Right? So you can kind of play this game. And in fact, this particular Petri net models a binary counter, right? So at the moment, so you can think of this as kind of displaying zeros and ones. At the moment, it's all zeroed out. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, and so forth, right? So this is kind of a binary. It's modeling a binary counter. But you can see that this behavior of this thing is kind of monolithic. So I wanted to come up with an algebra for these things to be decomposed into small components. And importantly, there's this word compositionality. I wanted this sort of way of decomposing to be compatible with the behavior. So like I could kind of recover the behavior of the composed net from the behavior of the components. So I was kind of happy with this. I was really proud of this paper. I had a paper at this computer science conference called Concur in 2010. And essentially, I'm not going to explain how it works because it's going to get a bit technical. But essentially, it's kind of like a decomposition to a monoidal category, right? So we have these. Can you see my mouse, by the way?
Yep, we could see.
Okay, good. So I can point at things. So you can see that this is kind of a composed net, and it can arise as a composition of these two components. And similarly here we have a decomposition. I mean, it's not really important that you understand the details, but you can give these components themselves the semantics, and then essentially when you compose the semantics, you get the semantics of the composition. So this was what was in my original paper, but then I thought, okay, this is still kind of monolithic in the sense that I would like to understand if this algebra of composition follows from something more primitive, something smaller. And very quickly, I kind of got to the realization that like all of the interesting things was happening on the transitions. And in particular, like transitions in Petri nets are kind of strange things, right? Because you can see that here, transitions can connect to, so the same transition can connect resources from two different places. But it can also, in this particular, this is not a very good example because in general, a Petri net can consume one token and produce two tokens, right? So it can kind of split off behaviors. So, oh no, I have to run for this thing again. I think by now you're getting sick of this animation. But basically, the idea is that kind of transitions themselves, you can think of them as having both kind of a sort of copying, discarding action and an additive action. Because they can sort of connect to many different things. So this is kind of like sort of like a copy structure, but they can also is sort of like two transitions can connect to the same place. So this is kind of an additive structure.
Oh, you just abstracted away the.
I abstracted away the places. So for now, I'm just talking about transitions. So like the most primitive algebra for transitions.
Lovely.
And somehow like the most natural mathematical setting to study these kinds of algebras, I thought were these things called props. So they were studied by Steve Lack in a very beautiful paper called Composing Props. So I'll tell you on the next slide just to sort of give you a little bit of background of what these props are. So props are symmetric strict monoidal categories with objects in natural numbers and with tensor product and objects being addition. More generally, Kyle props have a free monoid as a set of objects. And then one way to get props is via these things called string diagrams. Okay, so again, I don't really want to get very technical, but here's a simple example of a colored prop. So basically the generators are here at the top. And these are, in this particular example, we're going to construct as an arrow of this category the recipe for this dessert called crema di mascarpone. Okay, so for example, we have this whisk operation that takes 2 egg whites and produces a whisked thing. We have a beat operation that takes 2 yolks, sugar, and produces this yolky paste. We stir the yolky paste with mascarpone to get a thick paste. And then at the end, we fold the whisk whites into the thick paste to get the final dessert. Okay, so these are the individual operations. These are like, you can think of these generators of this thing. And then when I can wire these things up to obtain this string diagram, and this string diagram is now an arrow from egg tends to sugar, tends to mascarpone to crema di mascarpone.
Mm-hmm. Pavel, if I may interrupt.
Yeah, of
So
course, you can interrupt at any moment.
thanks. So for those who are new to string diagrams, how would you ask them to think about these? Like, what are
So
string?
so there's different ways to think about it. One way is to think about them. I think one good way to think about them is as operations that essentially transform resources to other resources. So it's some kind of a process, right? So in particular, so here it's a process that takes 2 egg whites and produces a whisk white. The cool thing about string diagrams, one of the cool things about string diagrams is it kind of forces you to take this resource sensitive approach, right? So you can't just arbitrarily copy things or discard things. They have to be explicitly in the syntax.
Right.
But I should mention that these are not just pictures, right? So originally I should have not deleted this, but originally on the slide I had a term that corresponded to this diagram, right? So these diagrams have a formal mathematical meaning, and they are not just pictures. So they're
They're
really
not
first class mathematical objects.
cool.
Okay, but anyway, so I want to go back to my research story. All right, so I started writing these equations for these transitions, and this equational theory for Petri nets seemed super ugly and complicated, and I was just getting really depressed. And then sometime later, in the spring of 2013, I was visiting Filippo Bonchi, who was in Lyon at the time, and he had just recruited a brand new, very brilliant PhD student called Fabio Zanasi, who's now a professor of computer science at UCL. And so we were actually looking for a PhD topic for Fabio at the time. So we thought, okay, these props and these kinds of equation theories, it seemed like a really cool thing to try to understand. So we started writing these equations for Petri nets, but then we sort of just gave up and said, they're too ugly. But somehow there was this weirdly beautiful structure that seemed to pop out, right? So essentially what we had, right, was this set of generators, and you can think of them as 2 pairs of commutative monoids and 2 pairs of commutative comonoids. So these altogether, these 2 monoids and these 2 comonoids are going to interact in interesting ways. Okay. And in general, there's like, if I just have one monoid and one comonoid, there's kind of 2 very classic ways that monoids and comonoids interact. One way is via so-called theory of bialgebra, or bimonoids, and these are these 4 equations here. Okay. Another way is via these things called Frobenius equations, and these are the Frobenius equations here. And this is like an additional equation that you often see in Frobenius theories. Some people call this the separability equation, or the special equation. Okay, yeah. So we kind of wrote, or we basically said, okay, we have this white monoid, this black monoid, this white comonoid, this black comonoid. And whenever white meets black, they interact like bialgebra. Whenever white meets white or black meets black, that's why these ones are written in gray, because they kind of are supposed to cover both cases. They interact like Frobenius. And then we thought, okay, let's just make things super simple. Whenever we get a diagram like this, they're just going to be equal. And when we get a diagram like this, it's going to be this. Okay. So we kind of thought, this just looks so beautiful that it must be something. But we but we had no idea of what it was, right? So then,
if I
yeah.
may ask, sorry. So from the Petrinet transitions, what do these white and black dots mean? Like,
Yeah, so because look, so let me try to explain this again. So so any place can be connected to more than one transition, right? So transitions should be able to kind of add up, right? So there's this kind of an additive structure, but transitions should also be able to split, right? So the same transition can connect to many different places. So this is this kind of a copy structure, right? So one way to think about this is you can always, whenever you see kind of whiten this talk up until the very end, when I'm going to, where it's going to mean something else, you can think of this as some kind of an addition. And whenever you see black, you can think of this as something like copying. But
Okay.
so addition typically goes from left to right, like as a process, right? It takes two arguments, produces one argument, and this is the zero. Copying also goes from left to right. It takes an argument and copies, or it takes an argument and discards. But now we also have the kind of a flip of both of these, and you can
Symmetry.
think of this in a relational way, right? So these are like taking the relation of addition and just flipping the relation, so taking the opposite relation.
Okay.
But at the time we didn't really have any idea. We just thought, okay, look, we have these two monoids, two comonoids. Let's write down these equations as they were meant to be. They just look so beautiful that they had to be something cool. But really, at the time, we had no idea what they meant. But we didn't give up because, like, we were kind of awestruck by the beauty of this, that it had to be something.
By the beauty of it.
Yeah, like sometimes you just go, this is too beautiful not to mean something. And it actually did turn out to mean something, because a few months later, Fabio was visiting me. I was in Southampton. I was a lecturer in Southampton at the time. So he visited me for a few weeks in the summer, on that summer, so just a few months later. And we basically put these equations up on the whiteboard, and we just stared at them for about a week without really making much progress. We just thought, what the hell is this? And then suddenly we had this realization that these are linear subspaces over the two-element field. And this just blew us away. And we very quickly proved that this was the case. So let me just remind you a little bit about what I mean by linear subspaces over Z2. So what's a linear subspace? So if V is a vector space over a field K, then a linear subspace is simply a subset of the vector space that contains the zero vector, is closed under a vector addition. So if U and U prime are in U, then also the addition is in U. And it's closed under scalar multiplication. So if U is in U and P is in our field, then the scalar multiplication of U by P is still in U. Okay, so just as an exercise, this is kind of an important exercise because I want to come back to it later. So okay, so R squared is an R vector space. What are its subspaces? Can you, Priyaa, tell me a subspace of R squared? So R squared is just a plane, right?
Yeah.
So now think about what needs to be in it. So what needs to be in the subspace, right? So zero. So the point of the origin point has to be in, right?
Yeah. The origin has to be in. Yes.
Yeah. So by the way, so that yeah.
Let's say lines through the origin, like all the lines.
All the lines through the origin. That's great. Yes. So all lines are examples, right, of a subspace.
Okay.
But there are two more. So that covers almost all of them, but there are two more subspaces that we haven't mentioned.
The origin itself.
The origin itself and the whole thing.
Okay.
Okay, and that covers the subspaces. So let me state you the theorem. Okay, so consider the free prop generated by this data. So essentially, what I'm doing is I'm constructing string diagrams from these gadgets. Okay, and I'm quotienting with respect to this equational theory that I showed you.
So you're just putting together the diagrams.
I'm putting all the diagrams, but I'm quotienting diagrams with respect to these equations, right? So these two things are considered to be the same diagram in this prop that I generate. Basically, I just generate. This is like generating an algebra, right? Like generating the free group, right? So you basically take all the terms from the syntax of a group, that has multiplication, has inverse, has identity, but then you quotient that syntax with respect to the equations of the group. So it's exactly the same idea, but here the syntax is diagrammatic.
Nice. Okay.
So it turns out that this thing that we get
Mm-hmm.
is isomorphic to the prop where the arrows are the Z2 linear relations. Oops. So these are precisely the linear so an arrow from M to N is a Z2 linear relation. And composition is just relational composition. Okay, so this is this weird correspondence. So somehow this just came to us suddenly in a flash. It was one of these aha moments, which was very nice. And we're kind of tried to think about what we can do with this. We actually ended up writing a paper, which was called Interacting Algebras and Frobenius. And this was presented at FOSSAX 2014. But very quickly, we kind of thought, there's got to be, this can't just be a fluke, right? There's got to be an example of something bigger. So in particular, yeah?
Something else is going on underneath.
Something else is going on here, right? So this can't be the full story. So we got very excited, and we wanted to understand if this idea could be generalized. And very quickly we discovered that this technique, I didn't really tell you about the technique because again, it would get a bit technical. The technique of how to get these equations. We had this kind of a basically like a methodology where we just like outputted these equations, right? So these equations came from some process, and then that process allowed us to prove that theorem. Okay, but I don't want to get into it.
Okay.
But anyway, this underlying technique actually works for any field, not just Z2, any field that arises in the field of fractions of a principal ideal domain. Okay, so the most canonical example, I guess, of such a thing is the rationals, which is just the field of fractions of the integers.
Oh, okay.
So we suddenly, using our let's say our technique, we ended up with this diagrammatic algebra that was able to describe any linear relation over the rationals. But this world of linear relations is very rich, right? And gives you a playground in which to explore linear algebra with string diagrams. And this is what ended up being called graphical linear algebra.
Wow.
So I essentially want to spend sort of the next section of the talk sort of trying to get you to see how you can do linear algebra with pictures like this, right? Because I at the time I got really obsessed with it. Like I spent so much time playing with diagrams and trying to understand what the hell was going on. But basically the whole story of linear algebra can now be told with diagrams. Okay, but first I need to kind of explain where the rationals really come from. And I think once you understand where the rationals come from, the rest sort of follows. Okay. So let's start by constructing the rationals. And the first step in our journey to get the rationals is to get the natural numbers. Okay, so essentially here on the left, I'm going to introduce this kind of a syntactic sugar where I'm going to tell you what each natural number is represented as a diagram.
Cool.
Right, and there's a kind of a almost like a good there's a good sort of operational understanding of this, right? Because what is zero? Zero is essentially this diagram that says, give me an input, throw it away, and produce zero. Okay, so that's the diagram for zero. Okay, so how do I get the diagram for k plus 1? Give me the input, copy it, do the diagram for k, and then add up the results, right? So it's kind of like I'm counting paths from left to right.
Nice. Yeah. By the way, this diagram that you have put in there, like the first diagram, it's used in quantum as well, right? Like to say like there is.
Yeah, well, I mean, so actually this whole system is, we discovered at the time, it's very closely related to the ZX calculus. So it's something called the phase-free fragment of the ZX calculus. So yes, these very similar diagrams have been used in quantum.
That's cool.
Okay, so what's the next step? So to get the integers, I need to add an additional gadget called the antipode. And you can think of the antipode as kind of a -1. It's a diagram for -1. So essentially, think of it as something that takes its input and multiplies it by -1. And we take the equations of algebra and add this equation, and this equation basically tells you that -1 plus 1 is equal to 0.
Oh, wow.
And these equations basically tell you that the antipode it behaves nicely with respect to the other stuff that's around, right? Everything, it just distributes over everything else. But together, the equations of algebra and this is actually known as the theory of Hopf algebra, right? So this is this famous Hopf equation, just written in diagrams.
Cool.
Okay, but now we have okay, so just as an I wanted to include this slide because I wanted to give you kind of a flavor of a proof using string diagrams, right? So I'm going to just prove now with all of just with the structure that we have now, that -1 times -1 is equal to 1. Okay, so this is -1 times -1. And I basically say, okay, well, the identity is just the same thing as the copy and the discard, and it's the same thing as add and 0, which we know is this by the Hopf law. Now I can associate the copy, right? I can associate the sum. I can pull, because the antipode behaves well with respect to everything else, I can pull sort of these two over the copy, right? But now I found an instance of the Hopf equation here.
Yep.
So that's -1 plus 1, that's equal to 0. And now this guy distributes over this guy. So I just get this, and I simplify to the identity. Okay, so this is an example of a proof by diagrammatic reasoning, just by using these equations and sort of applying them at various parts of the diagram.
So these diagrams actually encode numbers and like
Exactly. Yes. Yeah. So in particular, so we can get all the integers with just this, like, all the we already know how to get the natural numbers. I already showed you that. But then to get the negative integers, well, I just basically take my recipe for n and I multiply it by -1.
just
Okay, so
connecting
now
the wires is multiplying numbers.
just connecting the wires is multiplying, and in particular, there's a simple lemma that you can prove that so this is kind of encoding the algebra of the natural numbers or the integers within diagrams, that whenever I write this kind of a convolution-like thing, it's just plus, and whenever I follow them up, it's just times.
Nice.
Okay, so now I'm going to show you this equational theory for graphical linear algebra. Okay, so it's just as well as what we had before, right? But so everything is a monoid and a comonoid, and everything's commutative. We have these bialgebra laws in both directions. We have the antipodes. We have the Frobenius laws for when white meets black. And we have these additional rules for non-zero scalars. Again, I don't really want to get into the details because this is not really meant to be a technical talk. But again, kind of with this machinery that we discovered, we're able to prove that, again, the prop on this data, so this category that we get by just drawing string diagrams and quotienting with respect to these laws, is isomorphic to this category of linear relations over the rational numbers. So the prop where the arrows from M to N are just linear relations on Q to the N plus N, and composition is relational composition. Okay, and we published these results in the Journal of Pure and Applied Algebra. This is a paper called Interacting Hopf Algebras. Okay, so the rationals. How do we get the rationals? Well, P over Q is just because now we have, because we have everything sort of, you see that this syntax here is very symmetric. Everything that you can write from left to right, you can also write from right to left.
Yep.
So P over Q is simply sort of forwards P followed by a backwards Q. And again, just like we could encode the usual operations, the usual algebra of the integers within the diagrammatic syntax, we can rediscover rational arithmetic in this setting, right? So in particular, if I follow P over Q of R over S, then there's a very simple lemma that you can show that if Q is not 0, then these two things can commute. So Q can go past R like this. Okay, and this is just, we know that P followed by R is R times P. We know that S followed by Q is, well, I'm sorry about this, is S times Q. And so we've discovered just the usual formula for multiplying rational numbers, right? That P over Q times R over S is P times R over SQ.
Just by sliding the tiles over one another and fusing the tiles.
Exactly. And a similar thing can happen for, similar things happens for addition. So this, we're going to rediscover what we learned in primary school about how to add fractions. God, I keep doing this. Sorry, because I've cut my finger, so I can't really use my right hand, so I'm using my left hand, and my left hand sucks at this. So, okay, so P over Q plus R over S. So here we use this kind of a lemma. Well, we use actually an equation that because S and Q are non-zero, these two things simplify to identities. So we can just replace identities with these. Okay, so we multiply in, but then we know that SQ is equal to Q times S. So we can pull this across, and now we just get the usual formula for rational number addition, right? So we rediscovered the algebra of rational numbers just within our diagrams.
That's so cool. It feels
But at
natural.
some point,
yeah, right?
it's cool. I mean, it's really cool. It was like kind of like, wow, because actually we were kind of lied to when we were in primary school, right? Because the rationals are not as easy as we think they are, right? Like if you want to define them properly, they're actually equivalence classes, right? And then any operation, you need to show that it's well defined. Of course, we didn't prove this when we were in primary school. We were just told how to do it. But if you're going to do it properly, you have to prove that addition and multiplication are well defined. So this kind of gets around this and lets us rediscover this algebra of rational numbers within string diagrams. But at some point I had a moment of panic, right? This was I was really sweating at some point because everything's symmetric, right?
Yeah.
So in particular, I can turn 0 around.
So it's 1 over
somehow
0.
So somehow I have 1 over 0 in our syntax. So I thought, okay, there must be some mistake. We've stuffed up somewhere. The theorem can't be true. We failed. Because, we can divide by 0, so what the hell is going on? But then I kind of tried to understand. And let's recall the isomorphism, right? So these diagrams, all of these diagrams for numbers are diagrams from 1 to 1, from one wire to one wire, right? So if we follow the isomorphism, all these diagrams are simply linear subspaces of the rational squared. Okay? So in a way, what this algebra gives us here for these diagrams from 1 to 1 is kind of an extended version of projective arithmetic, right? Because projective arithmetic identifies numbers with one-dimensional spaces of p squared, which we already know, we've discussed before. These are just the lines through the origin. Okay, so for example, half is encoded as this line with slope half. 2 is encoded as line with slope 2. But also we have infinity, right? So 0 is the x-axis, but infinity is the y-axis. And this is precisely this 1 divided by 0. Okay? So you can make sense of the infinity with projective arithmetic, like so. But we kind of extend projective arithmetic, right? Because we can multiply, all the multiplication, like projective arithmetic typically says, well, you can't really make sense of what's 0 times infinity. But with this syntax, you can, because it's just composing these linear relations. So unfortunately, of course, composition of these additional elements becomes non-commutative, right? So, and particularly if I multiply 1 over 0 with 0, so if I multiply infinity by 0, I get this diagram, which is just a diagram for the 0-dimensional space, so just the point at the origin. And if I multiply the other way, so if I multiply 0 by infinity, I get this subspace, which is the unique 2-dimensional subspace, which is everything. Okay, so basically this kind of a weird divide by 0 arithmetic includes infinity and includes these two additional elements, which I usually call bottom and top.
Okay.
But you can write down the addition table, the multiplication table, everything. But of course, you lose commutativity of multiplication precisely because of this phenomenon here.
Only on these elements, right?
Yeah, I mean the rest is just the same as usual, is what you expect.
And also these represent kind of like the two extremities, isn't it? Like the spaces and everything is in between them.
Yeah. You're getting philosophical on me, Priyaa.
Sorry.
Okay, so I relaxed a bit. I kind of understood it and it was all fine. But the other cool thing is that this equational theory tells us some interesting things about linear algebra in general, right? So it tells us that every linear relation can be factorized as a span or a co-span of matrices. And actually, when you look at then the syntax of what these look like, it gives you two different ways of thinking about linear subspaces, right? So, and they both have this kind of a weirdly natural relation, operational interpretation, right? So on the one hand, this co-spanner representation kind of represents linear subspaces as solutions of lists of homogeneous equations. And the span view represents linear subspaces as linear combinations of basis vectors. Okay, and why is that? Well, you can almost kind of read the definition from these diagrams, right? So for example, this is the subspace, which is a subspace of rationals cubed, right? So there are three things where x plus y is equal to 0, and this is almost like you can almost read this off the diagram, right? X plus y is equal to 0, and z it doesn't matter. It can be anything. Okay, this is 2y minus z is equal to 0, so x can be anything. When we multiply y by 2, z by minus 1, we add them, and that has to be equal to 0, and so forth, right? So, but if let's say a variable might appear in two different equations, in that case, I copy that variable, and then these are the two equations that are involved. Okay, so we read these diagrams, kind of like the natural operational way of reading these diagrams is from left to right. And now let's look at these span representations. Now the natural way is to read them from right to left, right? So let's say I'm interested in all of the linear combinations of this vector 1, minus 1, 0. Well, I need to kind of generate an A, right? So if I read from right to left, this kind of says, generate me a number called A. Then copy that number, then multiply it by minus 1 in the second instance. And the third thing should always be 0.
Okay.
And here's another example. So this is B012. So generate me a B, copy it, and in the second instance, multiply by 2. And if I have two different vectors, then I'm going to need to generate two numbers. So generate an A and B, and then sort of wire them up correctly so that I get this description. Okay, so we started like just playing around and discovering interesting facts about linear algebra. I mean, in particular, one I think interesting, let's say, historical / sociological fact is that most linear algebra textbooks tend to concentrate on describing spaces or doing linear algebra using kind of basis vectors and emphasizing this point of view of linear combinations. But you can just as well do everything by talking about solutions of homogeneous equations. Okay. These two worlds are kind of equally powerful because anything can be put in co-span form and anything can be put in span form.
Okay.
So a little bit more linear algebra, so we can already sort of the graphical syntax can sort of encode a lot of interesting linear algebraic definitions. Sort of, it's already in the syntax, right? So I didn't really tell you how to do matrices, but this is kind of a generalized diagram here with multiple inputs and multiple outputs. So a diagram of this form represents a matrix. And then if I just plug into 0, then I get the kernel of the matrix. If I take the transpose of the matrix and plug the 0 on the left-hand side, I get the co-kernel. I get the image like this, the co-image like this, and so forth. And so this opens up the possibility of proving standard linear algebraic theorems using diagrammatic syntax. And I've played around with this, but this has been taken up by several people. I think notably João Paixão and other people at the Federal University of Rio de Janeiro. So there's some really cool, interesting papers that take up this point of view and do interesting linear algebra with it.
So you could go deeper into linear algebra using these diagrams.
Yeah, and João actually wants to like write a textbook, like a linear algebra textbook, just using strict diagrams, which I think is a wonderful idea. And I would read that book. So, okay, so that was, let's say, a very quick overview of that research adventure. Okay, so this takes us to sort of around 2015 to 2016. But we realized that actually, we can use this in lots of different settings. Okay, so first of all, linear algebra is a workhorse of classical control theory. So in particular, string diagrams, if we just interpret them instead of interpreting over the rationals, if we interpret them over a polynomial rings, then we get this very cute composition algebra of signal flow graphs. So in particular, you get string diagrams that look like signal flow graphs, but this kind of algebra that we have gives us a way of reasoning about them, reasoning about signal flow graphs within the diagrammatic theory without really needing to translate them into matrices, etc. Right? So Filippo, Fabio, and I wrote a couple of papers about this. But also I started working with an actual control theorist, and we thought about how this generalizes to sort of more interesting control theoretic cases, and particularly it does. So this was a kind of a really cool, let's say, sign that this diagrammatic approach had legs and could be used for different things. But then also we realized that these techniques go beyond just mere linear algebra, right? So we figured out that with Robin Piedlo, we figured out that we can do affine algebra. And then other people have done sort of graphical piecewise linear algebra. Just recently, there's been a paper on quadratic algebra, which is applications in probability theory. Maybe I want to say one more thing. So Guillaume Boisseau, he was a really brilliant student in Oxford, and he took this idea of affine algebra, and he realized that actually, if you look at sort of classical electrical circuit theory, it's really based on affine algebra. So his thesis was essentially redoing the kind of a standard first-year engineering textbook on electrical circuit theory using string diagrams, and you can really do, the entire corpus of electrical circuit theory just using diagrams. Except I reckon that you do it better because some of these theorems, so-called theorems in electrical circuit theory books, are actually a little bit hand wavy, and you do them properly when you do them with the diagrams. And also, sort of like the starting point, as you remember, was this idea of Petri nets. Well, we got back to the Petri nets. So there's kind of a canonical way to add state to these diagrams. And you get this very kind of a nice expressive syntax and a language for expressing concurrency. And in particular, you can play around with, you can actually sort of see Petri nets within the syntax, within this equational theory. So finally, we got to, let's say, addressing that starting point of this, what the hell this algebra of Petri nets could be.
Lovely.
Okay, so what happened next? So I had a wonderful sabbatical in Hawaii in 2016. So also, I think being in nice warm places tends to be helpful for mathematics. So that was that was really a lot of fun. So we were visiting Duško Pavlović, and at that point we were playing around with all of these different diagrammatic theories. But then we wanted to have a theory of these theories, right? So what kinds of things are these theories? And so we wrote a paper called Functorial Semantics for Relational Theories. So these were kind of theories that you can specify. So they all have this relational flavor, right? So it's always linear relations. There's always relations, affine relations, always relations of some kind. So we discovered that basically you had a functorial semantics, but instead of, let's say, the classical functorial semantics that takes the semantics in the category of sets, here the natural point, the natural sort of universe of semantics was the category of relations. That's why we call these things relational theories.
Okay.
And actually, it turned out that all of this, like this sort of meta theory of these things, was really closely related to the notion of Cartesian bicategory or Cartesian bicategory relations, which was introduced by Aurelio Carboni and Bob Walters in the 1980s, and a beautiful paper in the Journal of Pure and Applied Algebra. So also Filippo and I were really obsessed with this paper. This was kind of a joint obsession of ours. And one thing there kind of got us thinking, right? Because Cartesian bicategories were already known in a paper to be closely related to something called regular logic, right? So regular logic is the fragment of first-order logic where you just have existential quantification and conjunction. And coincidentally, or not so coincidentally, that's exactly how you do standard relational composition, right? So if you want to write the formula for composing two relations, that formula involves an existential quantification, right? Because it's, you know, like if I compose R with S, I have to find some point where they meet. So that's the exist and thing. So the formula for composing relations has precisely, you know, the existential quantifier and the conjunction. So we kind of got fascinated by this, by like seeing, on the one hand, we had all this kind of experience with doing things like linear algebra and related things with diagrams, but here we could do logic with diagrams. So we really started working on this. In particular, we got a new PhD student called Jens Zieber, and we had this paper on graphical conjunctive queries. So conjunctive queries is just what database theorists call regular logic. But this has kind of nice applications in database theory. So we really started thinking about logic and with string diagrams. And then sort of the natural question was to think more about logic, right? So around 2018, I was in Paris, and I was visiting Jean Krivine, and Jean Krivine told me this really fascinating thing, the story of C.S. Peirce and existential graphs, right? So C.S. Peirce was this polymath philosopher, mathematician in the 19th century, and he was an American. He never actually had an academic job, but he produced incredibly advanced mathematics for the time. And one of the final things that he did was these things called existential graphs. And existential graphs was around the same time that Frege was introducing the quantifiers. Peirce was playing around with these diagrams. So he really had diagrams that were encoding first-order logical formulas. And then he was like coming up with rules to transform these graphs that captured logical reasoning. And essentially, when you kind of squint your eyes at these diagrams, they are string diagrams, right? So C.S. Peirce invented string diagrams, 70 years before the definition of what a category is came around. Not to mention monodal category, right? So he was just like he was more than 100 years ahead of his time. And I became really fascinated with this, and then in 2019 I moved to Tallinn, and I was super lucky. I had sort of 4 very brilliant PhD students: Elena Di Lavoro, Maria Roman, Chad Nesta, and Nathan Hayden. And in particular, Nathan was a really interesting guy. So he was already an expert in Peirce. So he came from a philosophy background, and he was really interested in these existential graphs. And we tried to really understand, since they were basically string diagrams, we really wanted to present them properly as string diagrams. So we wrote this paper, Compositional Diagrammatic First-Order Logic, in this Diagrams Conference in 2020. And this continued, right? Because not long after Nathan started, Filippo recruited a brilliant new PhD student in Pisa, who's Alessandro Di Giorgio. And then sort of the final endpoint of the story is this thing that we published last year, which is called the Diagrammatic Algebra of First-Order Logic, which is like a proper algebraic presentation of first-order logic. And the interesting thing is we still have black monoids, black comonoids, and white monoids and white comonoids, except now the white monoids and white comonoids live on this black background. So it's a bit different, but you still see Frobenius equations, you still see much of the same structure, right? So somehow these 2 pairs of monoids and 2 pairs of comonoids interact together to produce us first-order logic, right? So this is kind of where we are at now. We're exploring the system, and we're very excited about it. So this is my final slides. I was over quick, but there's plenty of time for questions. So what are some of the morals of the story? So I really wanted to tell you kind of my own personal journey through this. So kind of on the mathematical, let's say, side of things, I wanted to really emphasize that I think string diagrams are a cool syntax that often gives you more of a high-level way of understanding computational algebra and logic. And I think we've discovered that time and time again through these various experiments that we've done. But maybe on a more meta lesson that I think I can take out of this is that it's very difficult to predict where research takes you. And I think that for this reason, the way science funding works these days is that it's very much tied to concrete projects, right? So you have to write a concrete project proposal. I'm going to do this and this and this and this, and this is work package 1 and work package 2, etc. And I think that this is somehow inefficient, right? Because often you can't really predict where research takes you. Often you have an idea, and great ideas should be explored. People should have the time and the freedom to explore their ideas without sort of being tied into these more and more sort of control freakery exhibited by grant funding bodies, where you have to sort of write quarterly reports about exactly how you've stuck to the plan that you've submitted 3 years ago, right? It's yeah. So that's my talk. Thank you very much.
All right, let's thank Paweł. Thanks for the cool talk, Paweł. I have questions, but I would just first open the questions to the audience.
I have so I don't have questions about the content of the talk, but I have questions about your last bullet point, since we were just talking about it. I would go one step further and say not just that it is usually inefficient, but it is exploitative of the researchers, and it is demoralizing to the researchers who are doing research or working on academic work because of their passions and not because of how they can contribute to the economy or whatnot. Even the use of the word inefficient is a bit utilitarian.
I absolutely agree. I mean, so basically, so the point at some point, I really, like when I told you that I really got obsessed with these diagrams for linear algebra. At that point, I was really depressed in terms of my career progression and the fact that we had to keep submitting these grant applications, and I kept getting knocked back at the time. So I just said, stuff this, I'm just going to write a blog. And so I basically started this blog on graphical linear algebra, and I had a lot of fun doing this, and yeah, no, but I absolutely agree with you that sometimes it can really feel like the system is designed to stop you from doing good research, and that's not the way it should be, and it definitely has also negative effects on morale and motivation and mental health and all of that. So I agree. So maybe I should have phrased this better. Yes, inefficient is not good enough.
Thanks.
Is it arbitrary how these projects are funded? Just
Well, I mean, I have to say that I now know also, I have much more experience in knowing how the how the pie is made, so to speak, because I often chair the computer science panels in the Polish grant giving agency. So I think everyone tries to do their best. It's a system in which the people who choose the grants are also trying to do their best, right? But I don't know exactly how we ended up here. I think sometimes I think we should try to. I mean, I wish that there'd be an experiment. So, for example, like instead of just forcing people to write these projects and having these evaluation panels, etc., just give out money randomly and see what happens. I wonder if you get better results.
Yeah, I agree. I think that I love the approach of experimenting with different different methods without feeling like we have to figure it out or we have figured it out. And in particular, I would say, following up on what Irfan mentioned, perhaps the thinking of the problem in terms of efficiency is making it worse, because it is foregrounding essentially the limited resources, right? Like the fact that there's no slack. So it sort of creates the incentive of putting the cart before the horse, as it were. Right? You have to be willing to spend without knowing what you'll get back, which is contrary to the idea of of efficiency. So perhaps it's important
Well, but
for
let's
us.
say, I mean, when I wrote inefficient, I mean, yeah, it's difficult to understand. I mean, so I meant inefficient for the progress of science, I think, fundamentally.
Right, right,
Let's
right.
say,
No, I completely, yeah, I understood it. I'm just saying in the ways in which we project our work to policymakers, or if we want to go in that direction, that it isn't about the best use of resources. It is about being more aligned with the process of creation. To see, in other words, what we do as more of a creative exercise, sort of like the way that people in the arts do more readily, where they don't pre-specify necessarily what the outcome will look like.
I
And
totally
I
agree.
think
I
this is
totally agree. Because also, well, I mean, I remember also writing this in the blog, right? Because as I said before, at the
Mhm.
time I was very demoralized. I mean, often these kinds of when you put together these kinds of, let's say, almost like game theoretic um frameworks, right? So like, essentially, in order to get a grant, you have to tick the right boxes. You have to satisfy certain criteria. You have to make sure your H index is such. You have to make sure that you've published at places X, Y, and Z. And often, the people who are very good at ticking boxes are not actually the people who you want to be in charge of doing the research, right? Because it encourages sometimes, like whenever you put together a framework of rules, even if you're doing it with the best intentions, these rules tend to create monsters, right? Because you have people who are very good at ticking boxes, and they're going to focus entirely on ticking boxes in order to kind of win the prize. Right? And you don't necessarily. I mean, ticking boxes is not what we want out of this, right? What we want is beautiful new research and new insights, and to further our understanding of the world. And somehow these things are difficult to quantify. And when people do try to quantify them, you create these pathologies. So I don't know what the right answer is, but it's clearly not what we have now.
Right. It strikes me that there is a mathematical structure to this argument, in the sense that, we do. I think I don't want what I was saying before to be misconstrued as implying there's no utility to setting up rules and systematizing things. But at the same time, while we do it, we shouldn't, conflate that with the with the thing we're after. These are just props in a way to get to where we want to go, and we know that we sort of we know we get to the right place when we surpass basically those scaffolds, if you will, right? Like, um, in other words, it's the exception that we are seeking, the thing that you weren't expecting. It doesn't mean that you shouldn't have had any expectations. It's useful to have expectations to be guided, but it's also important to know that your expectations will be proven wrong, and there's nothing wrong with that, right? Like you were saying before, Pavel, that you get something different out of it than you were expecting, and that surprise is actually useful. That's very motivating in some sense. We need to embrace that rather than penalize people for getting elsewhere from where they thought they were getting. I don't know if that,
Indeed.
yeah, Yorgo, you had
No,
your hand up before.
just a quick aside on the previous kind of argument about this decision making and the tick boxing is basically going back, sorry, to Plato and the ideal polis, where the people governing according to his ideas would be the philosophers and so on. So in this case, if it was the scientists that were making all these decisions, but anyway, yeah, sorry, just a thought.
Um,
Uh, On a related note, I would highly recommend Pavel's blog on graphical linear algebra. Graphical
Well,
linear.
by now it's 10 years old, right? So it's
That's all
so
right.
I
It's
think it's becoming a bit of a historical artifact.
really, I enjoy reading those pieces you're writing every time I read
But I
it.
did write. I do remember writing about this in particular. This idea of ticking boxes really had horrible side effects always, because you have you have there is a certain class of people that loves to tick boxes, and they're not necessarily the best research. Sometimes they are. Sometimes you have people who can do both. But but I often read. I mean, so for example, who was the guy who discovered the Higgs boson? I forgot his name, but I read an interview with him where he said that if he was now, starting a PhD, he would never have made a career in science, because this publisher perish environment, which, I mean, one of the things that we need to tick all the time is to have a constant output of publications. If you really focus on something very difficult, very ambitious, that's going to take you 15 years to do, and you really work hard for it, you can't do that in academia anymore. I mean, that's something that is just not possible. And of course, a manager might say, well, then how do I know that in 15 years you'll get a Nobel Prize? Maybe you won't, right? But that's the risk you have to take.
You're fun.
So I think the last thing you just said is an issue of trust in society, because okay, if a mathematician says that I'm going to spend the next however many years on trying out this idea, then unless we can show that the papers are coming out and so on, the funding agencies do not trust us to actually be working. Or in general, our society is not very trustful of people when it comes to topics of money. They don't trust their artists to just actually be working on the art. They need to be producing the art to show.
I think that's quite a recent phenomenon, no? It wasn't the case, let's say, 50 years ago.
I would tie it with the rise of capitalism everywhere at the levels it is right now.
We want research to be profitable.
Yeah.
Okay.
But now I'm a professor.
I feel like mathematicians should be trusted.
I'm a professor now, so I'm also part of the management chain. So I have to wear the other hats sometimes too.
You've been co-opted.
We all become the people we hated when we were young, eventually.
I mean, I think it's wise to see the other side, to see that the wisdom is in the middle somewhere, even though that's not sexy to say, but the devil is in the details. And as mathematicians, it appeals to me in some sense, right? You're not going for the easy answers, for the extreme answers. When you see that, that's not for you satisfying. Like, you want more. You dig deeper to say, what is that I'm not seeing? What are the interesting questions now? And I think, Paweł, I loved your talk. I must say, the structure of it. I know initially you were a little apprehensive. You were like, it's very.
Well, I've never given a talk like this before. It's the first time. So
I
didn't feel like
this,
me.
But aside from that, I mean, I noted that because it's interesting to pause it. Whether is it is there something wrong with foregrounding the eye? The perspective of the subject who's doing the math, which we don't tend to do, right? We tend to make objectified and distance ourselves from it. But specifically, the thing I'm pointing to now is the sense of flow, the sense of surprise and discovery that came through the repeated realizations you were having, that you were getting to a place different from where you thought you were going, and how often that was a result of interactions with new people. I mean, that came through very clearly, and I think it's a great lesson. For me specifically, one thing I wanted to bring up to you, since we have you here, is these connections as a teacher. Primarily now, I'm a teacher for the last few years, several years now. Even though previously I worked in math research, and I still try to stay connected, but primarily as a teacher, I have found these perspectives of in this case, the graphical perspective, but in general, the fact that we are trying to get to the ideas, behind the symbols in novel ways, as very useful and surprisingly so in conveying the freshness of mathematics to my students. I can't even tell whether it is specifically the diagrams that in some sense are more attractive, or the fact that they're a new representation. And I've used them. I've used both the blog and the diagrammatical description in teaching linear algebra repeatedly, and quantum information repeatedly, and to great success. They've always hit a nerve with students, and I think it's because, well, I don't know why, but for me, it feels as though it's like a wave of freshness in what otherwise might seem a very staid topic. Like here, in other words, where your mind is led to conflate the representation with the idea behind it, right? Like for decades, we were teaching, just to give a different example, you know, quantum physics using basically the same language. Keep saying the same equations, the same sequence of topics, and it was so easy for the students, for somebody who's seeing this for the first time, to not know what it is you're talking about. Are you talking about the equations, or are you talking about something else that the equations are trying to convey, right? Like conflating the syntax with the semantics, to use a different analogy, right? So the fact that with your research program, it sounds like it was unintentional, but you're certainly now very aware of it and playing and leaning into it. You're building bridges between, different new bridges between syntax and semantics, and as a result, showing connections, say, between algebra and logic, or between, information theory or computer science or dynamical systems, and algebras and so on. I mean, that is, in my mind as a mathematician, that's the lifeblood of mathematics. But it's very hard to convey to the students as a teacher, because you have to talk about the specific representations, and you spend so much time talking about the grammar, if you will, that you never get to that. So I'm loving that this, that in just only 10, 15 years, as you were saying, it's not a long time, that this approach, this nexus of people that you describe, have offered us such a rich new palette to play with. So it's been very useful for me.
Thank you. It's been really an exciting roller coaster ride, right? Like, but sometimes you just have to. I mean, as I said, like, I didn't know that this was going to happen. There was a lot of kind of very surprising realizations, and also it requires luck, right? You have to find the right group of people, and somehow all of this thing just the stars aligned. But I agree. I mean, it's been extremely exciting to sort of work on all these different topics that are seemingly unrelated, and find ways to connect them. It's been fantastic.
I mean, I loved you went and showed us, the algebraic structure of the rationals and additions, or something that, in other words, which can be used in classrooms at a very young age. That this is opening up, for example, a subject, a topic I'm very interested in and have been working with colleagues on for a while, are the difficulties of algebra as a language that everyone, literally everyone in the world, essentially, that has access to school is exposed to for years, and very few people really get to appreciate as something useful. And even students who are very good in algebra classes end up sometimes having difficulty applying it anywhere else, or seeing why it's a language as opposed to just a set of rules that you just follow. And so rethinking how we teach algebra has been something that's been a lot on my mind and my colleagues' minds. So something like this, just something like this, which taps not only on a different part of your brain, like the diagrammatic, the moving things around and so on, it's two-dimensional and everything, but also on computational resources, which to me, especially the younger people now, the younger students, are, it's much more natural for them to think in terms of computational structures, data structures and their manipulations, because that's how they grow up. They're intellectually evolved in that space, which wasn't my space, right? So I think we need to be thinking out of the box, in this way, that, so that they don't think about, x squared plus y squared equals z squared to be the Pythagorean theorem, right? In other words, the actual letters being names of things, Uh, one thing I said before in this group, and another Priyaa and Irfan have heard me repeatedly talk about this. One of the things I like about string diagrams, and more generally category theory, which is not really my background. I'm a probabilist by training, so I mean I've come to category theory late in life. But one of the things I like is that you never have to specify what the things are that move through the string diagrams, or like if you find yourself asking, well, what is it that you're talking about? You're missing the point. It's not about the thing. It's about how it acts and how it interacts, right? And so that's such a basic notion in mathematics, but we never teach it. Like you never actually explicitly hear any teacher tell you that, and it's a shame because as the hearer, as the student, you keep thinking, well, what am I missing here? What is it that I'm not getting? What is the mental representation I should have? And so these diagrams are great mental models to have, which evade that question, or, don't
I agree.
foreground it.
And by the way, there's a whole strand of control theory called the it was invented by a guy called Jan Willems, and it's called the behavioral approach, and it was essentially a very similar kind of strand of thinking in control theory, which is, by the way, very influential now. So also very much rejecting sort of this kind of ordained causal understanding of things, trying to really think of system as these interconnected networks that share variables. Heavy use of diagrams. So he has this thing called algebra of linking, tearing, and composing, I think. And so yeah, I was zooming, tearing, and linking. That's right. And in fact, that led that paper. So Paweł Rapisadle, who was one of the control theorists that I mentioned before, was a PhD student of this guy, and this is how we came together. So we sort of brought the string diagrams there, and it's very like it was an amazing experience, sort of trying to also understand this line of thought in control theory, which is very related to what you were saying.
Yeah, I did some work in control theory back in the day, in the early 90s. So I think I'm influenced. You can't shed that once you experience a system's way of thinking. And again, even then, as a graduate student, I remember being confounded by, what is it that's being moved about in systems? I mean, is it differential equations? Is it polynomials in some sense, in some complex variable? I mean, I'm, being more technical now, but essentially, I grew eventually to appreciate that it doesn't matter. It isn't the thing that's moving around in the circuit or on the strings, but it's what you do to it. It's the transformations and how they compose. It took me a while, and at the time, I lacked the categorical language. Yeah, Priyaa, this is in a sense, I'm shedding more light also in why I've been motivated to do this sort of work here now. And in other words, to foreground the utility of categorical thinking, in helping mathematical sense making, which is that it is a language that affords us the ability to think in this way, as opposed to, Paweł, like you were saying, the more deductive, sort of traditional representation of mathematics.
Yeah, it's interesting. The last talk, Bob also started his talk by saying like how the relationships are foregrounded, and it's not about the symbols like Hilbert, and he was talking about how Schrödinger saw quantum mechanics. Yeah. Okay. I think we have went past the time, but this is very interesting. Paweł, if you have a few minutes, I have a burning question for you.
Okay, but make this the last question because I really want to get home and get something to eat. It's almost 8 p.m. here.
Thanks for bearing with us. So I loved your presentation in the sense like it didn't foreground genius or like the mathematical nerdiness or anything like that, but it's like about the curiosity and the journey, right? And to be open to risks. Like we can make mistakes. So were there missteps along your research? Like
oh yeah, of course, many. You get stuck all the time. I think I mean I think what you said is right. So in a sense, I think I mean, I think fundamentally, I've always been a person who just wants to enjoy life. I think I'm a hedonist, and I think you know, what gives me the most pleasure in research is this process of discovery and understanding, right? So I think that's kind of a good way to do research in a certain way. It's like following what gives you pleasure is, I mean, tends to make you happier, I think, and tends to make you also more productive. And I don't know,
Motivated.
but of course motivated. But of course, yeah. I mean, there are also, I mean, with every high, there are also lows, right? There are weeks in which you hit your head against the wall, and then you finally discover that it was a wrong path. So yeah, I think that's also, I mean, coming back to the structure of this talk, right? So this is also what you don't get. You don't get papers about, we tried this for 6 months and it didn't work, right? That's not a publishable result. But it's very much part of the life of a researcher, right? So it happens all the time.
Hitting dead ends.
Yeah.
And then like keep walking.
And it's also a bit of I would also say it's a bit of a feature. I think we underappreciate it, but you couldn't have the highs without the lows. Really, you couldn't. And I mean, there's a pleasure to realizing that there's something more than what you thought. I mean, you know, because in a way, when you confirm that you were right, that's a very temporary thing. Then you start looking for the next thing. You know, it's almost, there's a disappointment to it, right? There's a anticlimax to, oh, that was all there was to it. Now I figured it out. It was just these three things. And then you want the next thing. So in some sense, you know, when you realize like that those subspaces were not numbers, they were, you know, they were not just projective. It was that, you know, that was actually, yes, a failure. You can see it as a failure of the original, the previous model, but in a way it was even better. Like you got to somewhere. So I think we underestimate the importance of being wrong in these productive ways, and we don't share it, and we don't have venues to share it. So I'm so glad, that this
Absolutely.
came.
I totally agree. Yeah.
All right.
Well, thank you, Paweł. Thank you so much.
Thank
You
you.
deserve to go get your dinner.
All right. Thanks a lot. This is a pleasure. Thanks a lot. Thanks for the invitation, Priya. Bye-bye.
Thank you, Paweł.
Thank you.
Bye. Thanks, everyone.
Bye-bye.